S2L26 is called data from surveys, and in 26.1 we're going to look at central tendency and proportions. So in statistics, the central tendency is the typical or central value in a distribution of data. So there's 3 different ways to measure central tendency that we'll look at, and it's mean, median, and mode. So you may have learned about those before. If you don't remember them, it's not a big deal. We're going to review them. So imagine you have a list of quiz scores for a group of students. That list includes 4, 6, 7, 7, 7, 8, 8, 8, 8, I don't know if I missed one in there, 9, 9, 9, and then 10. We're going to find the mean, median, and mode of the data set. Okay, so for the mean is the average of the data set. It's calculated by adding up all of the numbers in the entire data set and dividing by the quantity of numbers in the data set. So you'll see the formula for mean written is sometimes this way. This X over here, with the line over it, you just read it as X bar, and it just represents mean. So it'd be like saying the mean is equal to, you'd read it as X bar, and this symbol right here is called sigma. You'll see that more in the future. It represents sum, or it kind of means sum. So these two together, it's saying the sum of all the numbers in the data set. So you're adding up all the numbers in the data set. And then this n right here is the amount of numbers in the data set. So we'll say quantity. So quantity in the data set, or say the sample of the population or anything like that. Okay, so to find the mean, we'll say X bar, or the mean, is equal to, and then in the numerator, we're going to add up all of the numbers together. So I didn't want to write them because I thought they would get really messy, so I just typed them. So 4 plus 6 plus 7 plus 7 plus 7 plus 8 plus 8 plus 8 plus 8 plus 9 plus 9 plus 10. Sorry, it's kind of hard to say. And then we're going to divide that by the quantity of numbers in that set, which there's 13 numbers in that data set. So we'll say X bar equals all those numbers in the numerator. If you add them up, you get 100. And then divided by 13. So if we do 100 divided by 13, it ends up being a pretty long decimal, so we're just going to round it to 2 decimal places, and we'll say approximately. So 100 divided by 13 is approximately 7.69. So our mean is approximately 7.69. And then the median is the middle value of all the set numbers in the data set. So if the data set's not already listed from least to greatest, you do need to reorder it to find the median. I guess you can try without reordering, but it's not really, I feel like it takes longer that way than just reordering it. So the median is the middle value. What I like to do is I like to just kind of count down 1 on each side, just kind of maybe using a dot underneath each number. So 1 on each side until we get to the middle. Okay, and I'm just gonna count. I always trip out that I miscounted or something. So I have 1, 2, 3, 4, 5, 6 numbers on the left side, and I have 1, 2, 3, 4, 5, 6 numbers on the right side. Okay, so that 8 is the true middle. So our median is gonna be 8. So our median is 8. And then we can move on to the mode, which is usually the fastest one to find. So the mode is the most common value in the data set. It doesn't always happen in the middle. It can really just kind of depend. So if we look at how many of each numbers we only have 1 4, we have 1 6, we have 3 7s, we have let's see, 1 2 3 4 8. You don't have to underline them like I am. I just wanted to be a little bit more visual. We have 3 9s, and then we have a 10. So the number that we have the most of, that's going to be our mode, and we have 4 8s, so our mode is 8. Okay, sometimes there can be more than one mode. If there is, you don't like find the average of the two or anything, you would just list any or all of the modes that there are. So for example, like let's say there were also 4 10s, we would just say 8 and 10. Okay, moving down, proportions represent the number of units or individuals in a group that have a specific attribute relative to the total. So for example, if we had a sample of 303 people and we asked them to report their gender, of the 303 people in the sample, 145 report being women. What is the proportion of women in the sample? So in order to find, in order to find that proportion, we're going to set it up as a fraction. So we're going to put like what we're looking for in the numerator. So we're trying to find what the proportion of women is. So we'll say number of women. And then in the denominator, we're going to put the total. So however many people we ask or that are in the sample, we'll put that in the denominator. So number of women is, we said it was 145 reported being women. And then we asked 303 people total. So for the total in the sample would be 303. So 145 women out of 303 total people. And then we're just going to convert that to decimal and percent form as well. So if we do 145 divided by 303 to convert it to a decimal, ends up being approximately 0.4785. So that's a proportion of women that were in the survey. And then if we want to convert that to a decimal, to a percentage, you can either take the decimal place and move it twice to the right. So that would end up being 47.85%. Or the alternative way is if you take this number and, the 0.457, and you were to multiply it by 100, that'll give you the percentage version. So use whichever way you feel comfortable with and whichever way is like easier to remember. Either move the decimal place twice to the right or multiply by 100. Kind of one thing to like keep in mind, if you like when you're converting from a decimal to a percent, the number should get bigger. So like 47.85 as a percent versus 0.4785 as a decimal. If it gets smaller, then probably move the decimal place the wrong way or maybe divide it by 100 instead of multiplying. Okay, moving down to 26.2, we're going to start with standard deviation. So standard deviation measures how much data is spread out around that point, around kind of like the middle of the data set. So when data has a low standard deviation, they are densely clustered around the mean. So the lower the standard deviation, the more the data is like kind of organized around the mean, I guess, or just surrounding the mean in general. And then if the standard deviation is larger, that means that the data is like kind of more spread out from the mean. So you can see a few different visuals here. So in the first one, like on the far left, our mean is right around there at 8.82. And then the standard deviation 1.82 is relatively low. Like a lot of the data is around that middle, that 8.82. And then for the middle graphic, the mean is 6.64, so that'd be like about right there. You can see the standard deviation is higher than in the first graphic. It's 3.47 here, and the data is kind of more spread out. And then in the third graphic on the far right, the mean is 8.93, so it's like around right here. The standard deviation is really low. It's only 0.73. You can see like a lot of the data is right around that mean. Like it's very, very densely packed in there. Okay, moving down to margin of error for sample mean. So margin of error for a population mean will tell you the range of the population or that the population parameter might be in. In addition, it'll give you a level of confidence about this range. So the most like common, confidence interval that we'll use is 95%. So the formula for finding the margin of error for sample means is this. So it's margin of error within a 95% confidence interval is equal to 1.96. That's a number we'll learn more about in a future section, times S over the square root of n. So we'll go through one more time. So the ME is margin of error. The 95% is the confidence interval, meaning like whatever answer we get, we're 95% sure that our range will be within that. That'll make hopefully more sense after we go through some examples. Equals 1.96, that'll stay the same. And then times S, which is the standard deviation. And then over the square root of n, which is the sample size. And then, like I said, 1.96, we'll learn about that more in a future section, but it's based on the standard normal distribution. Okay, so example 1, a researcher measures the IQ of a group of 16 people using an IQ test. The researcher calculates a mean of 104 with a standard deviation of 14. What is the margin of error with the confidence level of 95%? So confidence level of 95%, that's already setting us up to use this exact formula. So we just have to figure out, okay, what is S, that's the standard deviation, and then what is N, the sample size. We don't have to do anything with the mean yet. We'll just kind of use it at the end to make sense of what we just accomplished. Okay, so we'll say ME, margin of error, the confidence interval of 95% equals 1.96 times, and then S will go in the numerator, and S is the standard deviation, and it says this right here, we have a standard deviation of 14. And then the square root of n goes in the denominator, and n is the sample size. So it says that a researcher measures IQ of a group of 16 people. So our sample size is 16, so it'll be the square root of 16. Okay, we'll just simplify piece by piece. We'll take the square root of 16 first. It'll be 1.96 times 14 over the square root of 16 is 4. And then we can divide 14 by 4, so 1.96 times 14 divided by 4 is 3.5. And then 1.96 times 3.5 is 6.86. So our margin of error is 6.86. And that's a number that kind of means it's the number that we vary from the mean. So since our margin of error, our confidence interval was 95%, it means that we're 95% sure that the population mean is within that 6.86 from the mean that we're given in the problem. So that means we can take the mean in the problem and add and subtract the margin of error. So the mean that we were given in the problem, that was 104. So 104 plus or minus 6.86. So if I do 104 minus 6.86, that gives me 97.14. And then actually I'm gonna write it out so it's a little bit easier to follow. So 104 minus 6.86 is 97.14. And then 104 plus 6.86 is 110.86. Sorry, I keep running out of room. So 110.86. Okay, so what the margin of error tells us is this researcher, they did a sample on just 16 people. And the margin of error takes that sample of just 16 people, and it gives us kind of an idea of how accurate this is if we were to apply it to an entire population. So the margin of error that we got was 6.86. And so we take that and we either subtract it from the mean to get the low end. So the low end was 97.14, and then we add it to the mean to get the high end. And then since our confidence interval was 95%, that means that we're 95% sure that the population's mean will be somewhere between 97.14 and 110.86. Okay, so sorry, it's kind of a lot. I will link with these videos, I'll link the workbook so you can see like kind of the full written out version as a guide as well. Okay, moving down to margin of error for proportions. So the margin of error and confidence interval for proportional data provides a range of confidence to estimate the true population proportion based on the sample data. So this is just for proportions as opposed to like just the sample mean. Okay, so our formula is a little bit different this time. It's the margin of error of confidence interval 95%. Still has the 1.69, and then it's going to be times the square root of p, that's the proportion, times 1 minus p over n. So I'll run through it one more time. That ME still means the same thing. It's the margin of error. And again, the 95% is the confidence interval, like basically how confident are we that this is accurate. And then equals 1.96 times p, which is the proportion from the sample. So p represents the observed proportion of our sample, over n, which is, I'm actually going to switch this color, sorry. So p is the observed proportion of our sample, and then over n, which is the sample size. So that means the same thing as our previous formula where n is the sample size. Okay, so example 2, we're going to apply this formula now. So 150 randomly chosen individuals were sampled on their eye color. Of the 150 individuals, 109 had brown eyes, a proportion of approximately 0.727. Find the margin of error for the proportion of people with brown eyes. So sometimes one of the hardest things with statistics is just figuring out like what we need to apply when. So before we actually do this problem, I kind of want to just compare these two. So in example 1, we were given the like sample mean, like we were given a like the researcher calculated a mean based upon his sample that he studied of 104. And example 2, we're given this proportion of that sample. So the first formula that we did up here, I know it says it in the title, but this is when we're given a like sample mean. And then this formula down here is going to be when we're given a proportion. I'm just going to underline the word proportion. And proportions will always be given to you. It'll be some number that's between 0 and 1, so some sort of decimal, just like we have here. Oops. Okay, so now we just have to figure out what each kind of letter represents in our problem. So we know P is the observed proportion. So in that, was that the second sentence? It says, of the 150 individuals, 109 had brown eyes, a proportion of approximately 0.727. So that 0.727, that's going to be our P, and notice there's two P's, it'll go in both spots. And then N is the only other thing that we need to plug into this formula. It is the sample size. So it says it in two places. It says 150 people were randomly chosen, so that's going to be our sample size. It also says it over here. We don't have to do anything with that 109. So we just need the total sample size and we need the proportion. So we'll put that 150 in for N. So it'll be 1.96 times the square root of 0.727 times 1 minus P again, so 0.727. And then over N, which is 150. Okay, and then we'll subtract inside the parentheses first, so we'll find 1 minus 0.727. So we'll do 1 minus 0.727. That ends up being 0.273. So for our next line, it'll be 1.96 times the square root of 0.727. And then times 1 minus 0.727 was 0.273. And then over 150. So next we'll multiply the numbers inside the, or not we'll multiply the numbers in the numerator of the radical together. I'm going to have to move this to the next line though. So it'll be 0.727 and then times 0.273. So I'm going to round from this point, so I'm going to change this to an approximately. So 1.96 and then times the square root of, I'm going to round to 3 decimal places, so 0.198 over 150. And then if you want, you can just leave this in your calculator. I'm going to clear it out. So it's 0.198, and then I'm going to divide that by 150 to simplify inside the radical. So it ends up being 0.00132. I'm just going to round it to 3 decimal places. So 1.96 times the square root of, it'll be 0.001. And then if I want to take the square root of 0.001, I have to switch like to the other side of the calculator, I guess, so to get my radical up there. So square root of 0.001 ends up being, if I round this one to 3 decimal places, that 6 that's in the 4th spot would round the 1 up to a 2. So this will end up being approximately 1.96. And then times the square root of 0.001 would turn into 0.032. So when you want to round to 3 decimal places, you look at the 4th spot, and since the 4th spot is a 6, which is 5 or more, it rounds the 3rd spot up to the next number, so from a 1 to a 2. And then now I can multiply those two together, so 1.96 and then times 0.032. So it ends up being approximately 0.063 if we round to 3 decimal places. Again, looking at the 4th number, which is 7. So 7 rounds the 2 up to a 3. So our margin of error ends up being approximately 0.063. Okay, I'm not going to go into the same detail as like the previous example as far as like applying that margin of error. But that margin of error 0.063 is going to be like, we're 95% sure that our like proportion from our sample is within this range of the actual like proportion from the overall population. It could be 0.063 below the proportion we have from our sample or 0.063 above. Anywhere within that range, we're 95% sure that the population of, or the entire population's proportion would be within that range. Moving on to example 3. Sorry, I had to add an extra line to the end of example 3 to finish out the problem, but it says a tire manufacturer produces 50,000 tires per week. With a margin of error of 0.2%, they expect that 1.5% of the tires they produce will be defective and will need to be returned to them by the retailers. What is the expected range of the tires that will be returned every week? So they're expecting like kind of like an average of 1.5% of tires to be returned, but their margin of error is 0.2%. So that means that it could be like maybe 0.2% less than that 1.5 or 0.2% more than that 1.5. So to figure out the range of tires, we need to do 1.5% and then plus or minus 0.2% to find that total range. So we'll separate it into 2. We'll do 1.5 minus 0.2%. 1.5 minus 0.2% is 1.3%. And then we'll also do 1.5 plus 0.2%. So 1.5% plus 0.2% is 1.7%. So between 1.3% and 1.7% of all of the tires they anticipate will need to be returned each week. And then if we want to find like the actual kind of quantity of tires that will be returned, it tells us at the very beginning of the problem that the manufacturer produces 50,000 tires per week. So we need to figure out what is 1.3% of 50,000 and what is 1.7% of 50,000. So to find that, I would do 50,000 and then times 1.3%, but I need to convert that to a decimal by moving the decimal place twice to the left. I would add a placeholder in there, and so that would become 0.013. You can also do 1.3 divided by 100 to convert it to a decimal, which it ended up being 0.013 as well. So we'll do 50,000 and then times 0.013, ends up being 650. So 650 is like the least amount of tires that they anticipate will need to be returned. And then to figure out what 1.7% of 50,000 is, we do 50,000 and then times 1.7%, but we need to convert it to decimal form first by moving the decimal place twice to the left, and we add a placeholder. That would become 0.017. So 50,000 times 0.017 ends up being 850. So 850, that's like the high range of how much they expect to be returned. So anywhere between 650 and 850 is the expectation. So we can say between 650 and 850 tires. So just to kind of run through that problem really quickly, they expect that 1.5% of the tires will be returned, but they have a 0.2% margin of error, so we have to kind of stray 0.2% above and below that expectation. So if we go below it, that's 1.3%. If we go above it, that's 1.7%, and that puts us at in between 650 and 850 tires. Moving on to 26.3, this is just going to be like a little note section. We're not going to do any examples here, but it's really just comparing sample size and margin of error. So if you have a small margin of error, then there's a small range in which your estimate of a population parameter might vary. This is the key thing that I want you to pull from this section. The best way to reduce your margin of error is to increase the sample size. So reducing your margin of error is a good thing. It means that like your results are going to be more accurate. And in order for your results to be more accurate, you need to increase your study, meaning that like you're researching more people, you're gathering more surveys, stuff like that, because the more like broad and kind of like well chosen your sample size is, the more it's going to represent the population. Okay, by increasing your sample size, you can have greater certainty of your sample estimates of population. So basically the larger sample size is, assuming it's like kind of the same, I guess, like organization or kind of diversity as your original sample size, if you make it bigger, it's going to be more accurate and it's going to give you a better estimate of the overall population.